Right, imagine the quietest place you can think of. Now imagine somewhere even quieter, so quiet that all the usual sounds of the world disappear. No cars, no wind, not even a whisper. But this deep silence is a bit of a trick in the quantum world. Even in the emptiness of space, at the very edge of what we can see, there's a subtle energy, a tiny quantum hum that never stops. This is zero-point energy, or ZPE for short. ZPE comes from the basic rules of quantum mechanics. This theory, which controls the universe at its smallest sizes, tells us that even seemingly empty space is buzzing with what we call virtual particles. These particles pop in and out of existence, constantly appearing and disappearing in a sort of quantum dance. Their super short lives aren't just a theory, they create a background energy that fills the universe. That's the zero-point energy. Understanding ZPE is super important for getting to grips with how the universe is put together. It's the lowest possible energy a quantum system can have. Even at absolute zero, when everything else freezes, this energy sticks around. This ever-present energy field has puzzled physicists for ages and has huge implications for how we understand the universe. Physicists used to think of zero-point energy, or ZPE, as a massive, flat sea of energy. This concept was rooted in the idea that even in a perfect vacuum, devoid of all matter, there still exists a baseline level of energy. This energy, they believed, was uniformly distributed across the entire universe, creating a vast, unchanging backdrop. This sea, while full of quantum jiggles, was thought of as pretty much still and the same everywhere in the universe. The quantum jiggles, or fluctuations, were seen as minor disturbances in an otherwise calm and uniform field. This perspective made it easier to conceptualize the universe as a stable and predictable place, where the underlying energy field was a constant, unvarying presence. But this classic way of thinking has run into some big problems, blocking our understanding of what ZPE really is and what it all means. As our scientific tools and methods have advanced, we've started to notice discrepancies and anomalies that the traditional ZPE model simply can't explain. These issues have forced scientists to reconsider and re-evaluate their long-held beliefs about the nature of this energy field. One of the main problems with this old view is that it can't explain how much energy is actually in the universe. When we try to calculate the total energy density of the universe using the traditional ZPE model, the numbers just don't add up. The predicted energy levels are vastly higher than what we observe, leading to a significant mismatch between theory and reality. Calculations based on this still ZPE model give us predictions way bigger than what we actually see. This discrepancy is not a small one, it's a difference of many orders of magnitude. Such a huge gap suggests that our understanding of ZPE is fundamentally flawed and that the traditional model is missing some crucial elements. This difference, called the cosmological constant problem, shows a big gap in our understanding of how ZPE works on a massive, universe-sized scale. The cosmological constant problem is one of the biggest unsolved puzzles in modern physics, highlighting the limitations of our current theories. It underscores the need for a new approach that can bridge the gap between theoretical predictions and observational data. Also, the old view struggles to fit ZPE into our understanding of gravity. Gravity, as described by Einstein's theory of general relativity, is a force that warps the fabric of spacetime. Integrating ZPE into this framework has proven to be a significant challenge, as the traditional model doesn't account for the dynamic and complex nature of gravitational interactions. Einstein's theory of gravity, general relativity, predicts that energy, including ZPE, should have gravity. This means that ZPE should contribute to the overall gravitational field of the universe. However, the flat-sea model of ZPE doesn't align with these predictions, creating a disconnect between our understanding of gravity and the behavior of ZPE. But a flat sea of ZPE would create a gravity field that would massively affect how the universe expands, and we just don't see that happening. If the traditional ZPE model were correct, we would expect to see significant gravitational effects that influence the expansion rate of the universe. The fact that we don't observe these effects suggests that our model of ZPE is incomplete or incorrect. These inconsistencies suggest we don't have the whole picture when it comes to ZPE, The traditional model, while useful in some respects, falls short of providing a comprehensive understanding of this fundamental energy field. It leaves many questions unanswered and many phenomena unexplained. The still flat C model, while a good starting point, doesn't capture how complex and dynamic this fundamental energy field really is. Recent research suggests that ZPE is far more intricate and variable than previously thought, with fluctuations and interactions that the traditional model can't account for. We need a new way of looking at it, one that matches the theories with what we see and reveals ZPE's true nature. This new perspective could revolutionize our understanding of the universe, providing insights into the fundamental forces that shape our reality and opening up new avenues for scientific exploration and discovery. Here comes the McGinty Equation, a groundbreaking theory that challenges the old view of zero-point energy. For decades, scientists have been puzzled by the enigmatic nature of ZPE, often visualizing it as a flat, uniform sea of energy that permeates the entire universe. The MEQ, however, gives us a fresh perspective on this mysterious energy field, suggesting that our previous understanding might have been overly simplistic. Developed by AI pioneer Chris McGinty in the 2022, the MEQ uses two key ideas missing from earlier models: fractal geometry and gravitational modulation. McGinty, a highly educated fine artist with a sharp interest in the intersection of mathematics and physics, spent the last few years developing his theory. Today, dozens of peer-reviewed papers have been published in leading scientific journals. Fractal geometry, often seen in nature, describes complex patterns that repeat themselves at different sizes. This concept is not just a mathematical curiosity, but a fundamental principle that can be observed in various natural phenomena. Think of a tree. Its branches look like the whole tree, just smaller. This self-similarity is a hallmark of fractal structures and can be seen in everything from the branching of rivers to the structure of our lungs. McGinty suggests this same principle applies to ZPE. Instead of a flat C, the MEQ suggests ZPE is a complex, fractal structure with fluctuations changing a lot at different scales. This means that ZPE is not uniform but varies in a highly intricate and dynamic manner. Gravitational modulation, the second big idea of the MEQ, suggests that the strength of ZPE isn't the same everywhere, but is affected by the local gravity. This idea introduces a dynamic interplay between gravity and ZPE, where the presence of massive objects can alter the energy landscape. Areas with strong gravity, like around massive objects, would have less ZPE, while areas with weaker gravity would have more. This creates a varied and dynamic energy field that is constantly shifting and changing. This dynamic link between gravity and ZPE is very different from the static picture of the old view. The traditional view saw ZPE as a constant, unchanging field, but the MEQ reveals it to be much more complex and variable. The MEQ, by using fractal geometry and gravitational modulation, represents a big shift in how we understand ZPE. It opens up new avenues for research and could potentially lead to breakthroughs in our understanding of the universe. By moving away from the simple idea of a flat C, the MEQ opens up exciting possibilities for fixing the problems that have bothered scientists for years. This new perspective could help resolve some of the inconsistencies and paradoxes that have long plagued the field of quantum physics, and paves the way for a deeper understanding of this fundamental energy field. The MEQ is not just a new theory, it's a paradigm shift that challenges us to rethink our most basic assumptions about the nature of reality. Imagine zooming in on a coastline that looks smooth from far away. From a distance, it appears as a simple, continuous line, almost like a child's drawing of the shore. But as you start to move closer, the picture begins to change. As you get closer, you see more and more detail. Little bays, rocks, and tiny bits of sand, each showing a new level of complexity. The once smooth line now reveals a rich tapestry of intricate features, each contributing to the overall structure of the coastline. This intricate detail, which you can't see from further away, is what fractal geometry is all about. Fractals are patterns that repeat at different scales, and they can be found everywhere in nature, from the branching of trees to the formation of clouds. The McGinty equation suggests that ZPE has a similar complexity, hiding a secret structure within its seemingly random fluctuations. Just like the coastline, what appears simple from a distance is actually a complex and detailed landscape when examined closely. Instead of being uniform, ZPE, according to the MEQ, forms a fractal landscape. This means that the energy distribution in the quantum vacuum is not smooth and even, but rather filled with peaks and valleys, much like a mountainous terrain. This means the energy in the quantum vacuum isn't the same everywhere. It varies, creating a dynamic and ever-changing field of energy that is far more complex than previously thought. Instead, it goes up and down, with areas of high energy next to areas of low energy, all linked together in a complex, self-similar pattern. This fractal pattern means that no matter how closely you look, you will always find more detail, more structure, and more complexity. This fractal nature is really important for understanding ZPE. It provides a new way of looking at the quantum vacuum, not as a uniform sea of energy, but as a rich and varied landscape. It suggests that the energy in the vacuum can change dramatically at different scales. This means that the behavior of ZPE can be very different depending on how closely you examine it, revealing new properties and behaviors at each level of magnification. What looks like a flat sea from far away might reveal intricate patterns and fluctuations as we look closer at the quantum world. This zooming in process is much like examining the coastline, where each new level of detail adds to our understanding of the whole. This insight could be the key to unlocking ZPE's true potential. By understanding the fractal nature of the quantum vacuum, we can begin to explore new ways to harness this energy, potentially leading to breakthroughs in energy technology and other fields. By using fractal geometry, the MEQ gives us a more accurate and detailed picture of the quantum vacuum. This new perspective allows scientists to develop better models and theories that can explain the behavior of ZPE more precisely. It moves us away from the simple idea of a uniform energy sea and shows us a world of complexity waiting to be explored. This complexity is not just a curiosity, but a fundamental aspect of the quantum world that can lead to new discoveries and innovations. This complexity, rather than being a problem, opens up new paths for research and might hold the answer to some of the universe's biggest mysteries. By embracing the fractal nature of ZPE, we can unlock new potentials and perhaps even solve some of the most profound questions in physics.